Hello and welcome to exercise 2, chapter 6. This is an exercise that is based on the setup that was introduced to us in the previous week in chapter 5, exercise 4, where we had one policy that we were looking at, and this policy had in observed claim sizes x1 up until xn, and the assumption was that given theta, each of these were IID Pareto distributed with this tail distribution. And also we assumed that theta was gamma distributed. And we were looking at the heterogeneity model. What we then did in that exercise was to say, well, let us consider each of the x's and we will reinsure our losses in the sense that if a loss exceeds a level K, which we also call a retention level, if it exceeds a level K, then that loss will be covered by a reinsurance company. And whether or not a loss is covered by a reinsurance company, we then modeled that using the stochastic variable yi. Simply, it is switched on if the loss exceeds k, it is switched off, so equal to 0 if the loss does not exceed k. And we also established that then the yi's were IID binomially distributed with success parameter, or success is when the reinsurance company covers. So with success parameter given by the expected value of y1 given theta. In exercise 4 in chapter 5, we calculated a Bayes estimator of the yi given theta, of the mean of yi given theta. So we calculated a Bayes estimator for this thing here. It was some kind of fraction between sum of logs of x's. What we want to do in chapter 6, exercise 2, is we want to calculate a linear Bayes estimator and the corresponding Bayes risk based on the data x1 up to xn of the same thing. However, we are kind of in a funny dilemma conundrum situation because the question is, when we want to calculate a linear Bayes estimator of this thing, well, then we want to find the expected value of y1 given theta, right? Do we then want this linear Bayes estimator to be a linear function of x1 to xn, or do we want it to be a linear function of y1 to yn? I mean, if it is a linear function of y1 to yn, then essentially it will still be based on the data x1 to xn because the y's are derived from the data. On the other hand, if we want to write it up as a linear function of the x's, then we're kind of in trouble because the x's operate on another size scale than the y's. I mean, the x's are Pareto distributed, whereas the y's are somewhere either 0 or 1. So the expected value of y given theta will be somewhere between 0 and 1. So we just kind of agree with ourselves and each other here that we want to find, the the linear Bayes estimator p hat for p of theta expressed as a linear combination of y1 to yn, where the yi's are each equal to the indicator of xi given greater than k, and in that sense we will have a linear Bayes estimator which is based on the data x1 to xn, however it will not be linear in x1 to xn. So by theorem 631, I think I accidentally wrote theorem 642 earlier. Have to correct that in some comment of some kind. Well, in theorem 631, we have that the linear Bayes estimator is given as 1 minus W mu plus W multiplied by the average of the outcomes. And also that the Bayes risk written as rho of mu hat LB, the Bayes risk, the linear Bayes risk is given as 1 minus W multiplied by lambda. So we will have to calculate these two things here. And as we might recall from exercise 1 that we did earlier, calculating W involves calculating certain other things as well. So let us just write up here. We want to calculate p hat, which is equal to 1 minus W multiplied by mu plus W multiplied by y bar, where y bar is the average of the y's, which in turn each is an indicator based on x. So we will just write that up. This is 1 over n multiplied by the sum of j equal 1 to n of the indicators of each xj being greater than k. So now we want to figure out what W is and what mu is. So we will just start from one end and work towards another. Mu is given as the mean value of the thing that we're trying to estimate. So the mean value of P of theta. Now this is also the mean value of the mean of y1 given theta. And note that we want to write this up based on the x's. So we just recall that y1 is an indicator function of x1 being greater than k. And when we take the expectation of an indicator, it's the same as taking the probability of the indicated event. So it is the probability that x1 is greater than k given theta. Take the mean value of that. And when I take the expectation of this, I kind of smooth the theta out, right? So I have the probability that x1 is greater than k here. So now I have the mu, I want to figure out the w, and we recall that w is equal to n lambda divided by n lambda plus phi, and we then have to figure out what phi, respectively, lambda are. Well, let's just start with lambda then. Lambda is equal to the variance of p of theta, which is then equal to the mean of the second moment of p of theta. So the second moment of p of theta, sorry, minus the first moment of p of theta squared. Now the first moment of p of theta we have already found, so this is just the probability that x1 is greater than k squared. So the thing that we want to figure out is what is the mean of p of theta squared. Now the mean of p of theta squared. Well, let us try to write up the definition of p of theta. It was equal to the mean of y1 given theta, and in turn equal to the probability that x1 is greater than k given theta. So what I have is the mean value of the probability that x1 is greater than k given theta squared. Now recall that x given theta was Pareto distributed, and that means that I actually have an expression for the probability that x1 is greater than k given theta. That is exactly what I have up here with the tail probability. So I can just plug that in, and then I have lambda divided by k to the theta to the second, so to the 2 theta. Now I want to figure this mean value out, and I can do that because I know that theta is gamma distributed and which parameters it is gamma distributed with. So here I just simply calculate an integral where I have lambda divided by k to the 2y multiplied by the density of theta, which was the gamma density with parameters gamma and beta evaluated in y dy. Now I can kind of rewrite this a little bit. So let me just try to write out, first of all, the density of theta. It is equal to beta to the y divided by the gamma function evaluated in little gamma. And then we have y to the gamma minus 1. And then we have e to the minus y beta. Now, I kind of want to fit this lambda over k to the 2y into this mold because maybe then I can identify some gamma, move something around, stuff like that. So I do a trick where I realize that x is equal to e to the log x because the exponential and the log just cancel each other out. So here I take e to the log of this expression, which is e to the 2y log lambda over k. Now, the smart thing here will be if I can have minus y somewhere in this exponential, because then I can maybe put these two terms together and recognize some form of gamma density. So I want to do that. And another thing that I notice is that uh, that probably means that this beta parameter will change. So under any circumstance, I should move out the beta parameter. And then here I have something divided by gamma of gamma. We'll figure the rest out soon. I have y to the gamma minus 1, and then I have e to the minus y. And then I have beta. And essentially what I can do here is I can switch the division order of lambda and k. So I have log of k over lambda, and I can pay for that by a minus out here. And then what I have is beta plus 2 log k over lambda dy. And see, what I can do here now is I can kind of notice that this thing here is my new second parameter. So I can plug that in over here. Sorry, this isn't supposed to be beta to the y, it's beta to the gamma. Yes, I can plug that in over here. So it is, and this is also beta to the gamma. So I can plug this thing here, beta plus 2 log k over lambda, all of this to the gamma. But in order to multiply this into the expression, I have to divide by this as well. So essentially, I have just multiplied by 1. Okay, now what I have inside the integral is just a gamma density, so the entire integral evaluates to 1, and what I am left with is beta divided by beta plus 2 multiplied by log of k over lambda, and this entire fraction to the gamma. If I divide through it all by beta, then what I end up with is 1 plus 2 log k divided by lambda over beta, all of this to the minus gamma. And that is very nice because then I also have an expression for the second moment of p of theta. So let me just write this here. The second moment of p of theta is equal to, I'll just remove all of this because then we can kind of have an overview in a second. The second moment is equal to 1 plus 2 log k over lambda divided by beta to the minus gamma. And then I can continue calculating because what I want now is I want to find my phi, and my phi is equal to the mean of the variance of uh, of y1 given theta. And y1 given theta, we recall, was binomially distributed. Sorry, the y1 given theta, not just y1. So y1 given theta is binomially distributed. with these parameters, and hence its variance is equal to p of theta multiplied by 1 minus p of theta. And what we see now is I get the mean of p of theta, which is equal to mu, and which I have an expression for, minus the mean of p of theta squared, which is equal to this expression that I have just found. So that's very nice because that means that all in all, I also have an expression of phi, given as the probability that x1 is greater than k, minus 1 plus 2 log k over lambda divided by beta to the minus gamma. Okay, so now I have all of these expressions. So in order to obtain the Bayes estimator in the more or less linear case, all I have to do is just plug these expressions into the formula for W and plug them into this formula to get the result. Now let us just do that for fun. So the result is that p hat is equal to 1 minus w, which is n multiplied by lambda, which was this thing here. You know what? It's not fun. It's not fun to plug all of this in because it's just a mess, and it's not pretty, and it's not nice to look at. So I'm not going to plug it in. But you can do it, and you can also do it for the linear risk. However, the thing that we have to do as well is we have to kind of compare this with the Bayes estimator that we found in chapter 5. Now, there's one thing that is certain, and that is the Bayes estimator we have found in chapter 6 is not linear in the x's, in the same way as the Bayes estimator that we found in chapter 5 was not linear in the x's either. However, the Bayes estimator we have in chapter 6 is linear in y. It was not linear in y in chapter 5. So that is one thing we can conclude. Another thing that we can conclude is that whatever values we gain by plugging in w and lambda here, the Bayes risk in this case will always be greater than the risk that we found in chapter 5, because here we are minimizing over a smaller family of of functions. So that is another thing that we can conclude. I'm sorry to say that we cannot conclude that much more, but I guess that is also enough for today.